long Thanksgiving weekend. Meeting is being recorded. All right, here we go. Now I see Maryam just joined in. Maryam, did we talk about the presentation today?
Yes, we did. Good
Okay,
morning.
will you be ready for it later?
Yeah, anytime.
Yeah, so let's just check if your slides come through. Let us check that first.
Okay. So let me forward that to your email. What I did send was the whole proposal.
Yes, okay. Or do
Yeah.
you want to share? Can you share?
Yeah, I can share.
You cannot share.
Oh, I
Shane,
cannot, right?
Shane, if you're in the call, can you make Miriam Alka a co-host?
Yeah, for sure. We'll do that right now.
Thank you.
There we
I
go.
think I'm already sharing, right?
Yes, you're sharing. Oh, this
Yeah.
works fine. Okay. Miriam, where are you in the world?
I'm currently in the UK.
In the UK, okay. But you're
Yeah.
from Nigeria, as I see.
Yeah, I'm from Nigeria.
And where in the UK are you?
In Birmingham.
Birmingham, okay. All right.
Yeah.
Yeah. So we have two of these presentations today. The first one will be by Katarina, and then
Okay.
you will be the second one.
All right, no problem.
Okay.
So I can stop sharing, right?
Yes, you can stop sharing.
Okay.
And then there was a third student who said she might do that. Halima, is Halima here? No, she's not here yet. I don't see her on the list. Okay, maybe she comes in later. So, okay, let's slowly get started. So today is a special day because we have two Blitz presentations. Blitz presentations are short 4 or 5 minute presentations of students who take this course for credit. And so this is one of the things they do to get a credit for this course. The idea is the students will work on a project for the entire term, and at the end of term they write a report. But as an intermediate milestone, we get this Blitz presentation, so we all know what they're working on. And they also submitted a little research proposal of the ideas they have to work on this. After that, we have two of those today. After that, I will talk about parameter estimation. So that's a very different, but very important topic as well. So we have to cover it at some point, and I'm going to start that today. Now, today I'm still remote in Edmonton. On Thursday, I will be back in person at the Fields Institute. All right. So we start with Katarina. So then, Katarina, I need to upload your thing.
Should I stand up?
Actually, it's better if you sit. Then
Okay.
the microphone is right in front of you. That will work fine.
Okay, cool.
Share screen. And we can also see you in one of the cameras, so that's perfectly okay.
Okay.
And this is this. Hold your horses. Yeah, so there's a presentation, and there's the second page. Good. Go back there. Good. Our first Blitz presentation is by Katarina Saka. Please go ahead, Katarina.
Hello. So I have proposed for this semester that I will be modeling treatment-resistant cancer cells and inflammation. Told me to sit. Oh, that and yeah, so the effect of inflammation on cancer, right? So initially, our bodies are always fighting off illnesses and things, and so inflammation works against cancer. But at a certain point, that kind of switches, and it starts to promote cancer progression, metastases, and it can increase the risk of reoccurrence. It can foster proliferation. And so we need to know how cancer really is interacting with inflammation. And that was and has been well studied on the next slide by Wilkie and Fariana. And they modeled the effect of inflammation on a single tumor's growth, specifically in the case of Lewis lung carcinoma. So in this model, we have that cancer, denoted C, is growing logistically. And then there's a term for chemo, and then inflammation is growing as well logistically, but there is an interaction between I and C, or not an interaction, but an effect from the cancer on inflammation, right? So it's spiking your immune system. Next slide.
Mm-hmm.
And this is the full model, right? So we see that the carrying capacity C is dynamic and it depends on inflammation and cancer. And then the final equation is just for chemo. But yeah, so that's that one. Can I have the next slide? And so what my proposal is that rather than thinking of cancer as just one type of cell, right, to split it up into susceptible cells and treatment-resistant cells. And so then that first equation looks like this. And I highlighted the competition terms, right, where we have competition between the susceptible cells and the treatment-resistant cells. And so, yeah, and then we also have that mu1 is going to be greater than mu2. So the effect of chemo is going to be greater on susceptible cells than it would be on resistant cells.
Nice.
And,
Oh, sorry.
and so, yeah, this is the final, and this is the full model. So everything else stays the same because we're talking about the same tumor. So we don't need to add in any new things. We just need to consider the difference between a susceptible and resistant cell. So next slide, please. Thank you. And so the general research questions that we can answer with this is how does the growth of cancer change from the model by Wilkie and Fariana compared to this model? And so then we can also investigate how the growth of the treatment-resistant cancer cells change if we totally eliminate inflammation, as well as if we only just limit it with something like an anti-inflammatory drug. And yeah, so those are the kinds of things that we can model. And so generally what we want from this is to just learn and quantify how treatment-resistant cells, cancer cells can respond to inflammation. And this is really important because treatment-resistant cancer cells can end up leading to there being cancer cells that are left over. And so that can lead to cancer progression and recurrence later on. And so it's important to understand how the body interacts with cancer. And so that's why we're looking at inflammation. And yeah, that's it.
Excellent. Thank you very much. So we are all clapping. You can see me, but you can't see the others. Very nice. I like this idea a lot. This is really cool. So if you want to show your appreciation and respect for Katarina's work, it's a good idea to ask questions. So if you like somebody's work, the best compliment you can make is to ask questions. So let's open the floor for some questions.
There's a question that what is the measure of inflammation? And so it's just the volume of immune cells that are present. That's how the author did it, or the researcher did it in Wilkie and Fariana. So that's the way that I will be doing it as well.
Very good. Other questions?
So I have several questions. One is the microenvironment interaction. If you could take it explicitly. And the other one is your 4 points at the very beginning of inflammation supporting or encouraging cancer in different aspects. Could you take all of this in the equations?
I think that a lot of them you can consider in these equations, like tumor progression and risk of reoccurrence and proliferation, but I don't think cancer metastases you can model with this specific model because there is no spatial component, and it's limited to only one model. It's one tumor. And what was your other question?
First question.
Yeah.
Happens in a tissue. So it doesn't know exactly what is tumor, what is microenvironment.
Yeah, it doesn't. It's just from what I've seen in the research is that the tumor can kind of, or the cancer can kind of co-opt some of the things that are present with an immune response and can kind of use it for its own benefit to proliferate, like use it as signaling pathways. Yeah.
Very
Yeah.
nice. So I have a question too, Katarina.
Okay.
The split up into sensitive and resistant cells, is this a new idea, or has this been done by Wilkie as well?
I didn't see her do it, but
Yeah, which
yeah.
is great. So this makes it
Yeah.
even more exciting. Wonderful.
Yeah.
So yeah, I like it a lot. This is great.
Thank
Are
you.
there any further questions? I don't see the chat. Maybe this is the chat. Okay. Chat is good. Yeah, all right. Then I stop sharing this, and thank you very much again, Katarina.
Thank you.
How do I do that? This way. Stop share. And then we can move over to Maryam. Maryam, would you share your slides?
Okay. Okay, so
Yeah, so then the next talk is by Maryam Alka, and she will talk about, what will you talk? About hypoxia. Oh, interesting. Go ahead.
yeah. Hello, everyone. So this is my grant proposal for I intend to work on the mathematical modeling of tumor dynamics in hypoxic environment for optimized cancer treatments. So I start by introducing hypoxia, which is low level of oxygen, and is a common condition in tumors, which can lead to therapy resistance and affect the cell death or survival. So in real tumors, hypoxia typically refers to oxygen concentration. And for the purpose of this experiment, we're going to be considering paclitaxel. And the choice of paclitaxel is because of its favorable profile. It's really safe to some extent. So we're going to be considering paclitaxel. And then it's widely used in the treatment of breast cancer, ovarian, and lung cancer, but is less effective in hypoxic environment condition. So the research will address this by developing a model to predict the drug efficacy in hypoxic tumors. So this is just the background. We know cancer cases keep rising globally, but in sub-Saharan Africa is disproportionately high compared to the mortality rates. And so in my own thinking, I feel this has to do with the data, because most of this data are gotten from the high income regions and then making it less applicable to African population. So we need to understand the local factors that influence cancer behavior. And this is really important.
Nice.
So this is just like a chart of like a statistics of the cancer. The blue one is the global cancer cases, new cases. Then the red one is the mortality rate globally. Then you can see the green and the yellow are really close. So the number of new cases and the mortality are very close, which is not too good. So here there are existing models, but these models tends to overlook the interaction between oxygen diffusion and the drug gradient in tumor dynamics. So, and without accurate modeling, treatment strategies are often suboptimal. So in order to address these gaps, we're going to develop the model, a mathematical model of tumor growth, and subject to treatment with paclitaxel under hypoxic conditions. Then we validate the model through cell culture experiment, and then we conduct sensitivity analysis in order to identify the key parameters in the model. Then we extend the model to investigate combination therapies to improve the outcome. So some of the existing models that are out there are the logistic, the Fisher, Kolmogorov, the Gomperzian, but they all fail to capture the interaction between these variables. So our model will integrate these variables such as the oxygen diffusion and the drug gradient. So we're going to use Hill function and Michaelis mentioned to better capture the nonlinear relationships, if any, between this. And then we use machine learning technique to refine the model parameters. Then, okay, so this has all been, we use cancer cell lines exposed to hypoxic condition and treated with paclitaxel. And then we use the data from the experiment to calibrate the mathematical model. After that, we identify the parameters affecting the tumor response to treatment. And then we propose optimized treatment regimes, including drug combinations and dosage. So the model will simulate paclitaxel with other treatments, such as radiation. That is, if we're able to capture the dynamics in the first instance, then we go further to extend the model to capture combination therapy. And then we explore the synergy or the antagonism between the combination therapy in hypoxic environment. So this research will tailor treatment strategies for cancer patients in low resource settings, and then it will bridge the gap between cancer treatment outcomes in low and high income countries, and then potential to reduce cancer mortality and improve survival rate. Then in terms of equity, diversity, and inclusion, we intend to prioritize recruiting underrepresented groups, which are the women and minorities in STEM, and ensure the findings are applicable across diverse population. And then we intend to render mentorship opportunities for underrepresented groups as well. So, and then this is how we intend to utilize the budget of the 100,000 grant. So we intend to use 20,000 for personal and research assistant salaries, computational resources 20,000, and the laboratory equipment and consumables 35, travel and conferences 10, miscellaneous, and then the institutional overhead deduction will be 10,000, making everything 100,000. So in summary, this project will develop a mathematical model for improving cancer treatment in hypoxic environment. And then the tailored treatment will reduce trial and error in chemotherapy. Then, thank you very much. Here are some of the references I used. Thank you.
Thank you a lot. Thanks a lot, Maryam. This was also very awesome. All are clapping. Can you go back to the reference page? I just want to have a look there.
All right.
And then we invite for questions. Any questions?
Hello, can I ask one?
Yes, please.
Thank you, Maryam.
All right.
I have one question. So you were proposing that there would be a relation between oxygen diffusion and drug. I forgot the term. What was it? Drug orientation?
Paclitaxel.
Paclitaxel is a chemo drug.
Okay, yeah. So how are these two things related? Because I am not aware of these terms. So I just want to know like how oxygen diffusion and drug are related. If you want to model it mathematically, so how will you
okay, so
model
like I mentioned earlier, hypoxia refers to the concentration of oxygen in tumor.
Okay.
Yeah. So sometimes, when the cancer cells keep proliferating, it goes out of oxygen, or the tumor becomes low in oxygen, and then sometimes this low oxygen level tends to affect the efficacy of the drug.
I see.
Yeah. So we intend to capture this relationship using either Michaelis-Menten or the Hill function, which Michaelis-Menten is also a Hill function, but a special case with the Hill coefficient as one. Does that answer the question?
Yeah, thank you.
All right. Thank you.
Okay, are there other questions?
I had a question on the chat. It was about the graph that you provided for the African, that one. So those rates are very, very low. Are they significantly lower than what you would expect given the world population?
No, they're not significant. They're not low, because when you compare it to the global, the African new cancer cases represent about 7.2% of the world's cancer new cases, which is quite large. And looking at
Proportional to the population.
Yeah, proportional to their
Okay.
population.
So
Yeah.
the issue is the deaths is also quite high near it.
Yeah, it's really high. And then when you compare the statistics of the new cancer cases in Africa, and then the mortality rate as well, you can see they're very like close.
Mm.
Yeah, so which is not good enough. At least there should be a significant difference if really the treatment is working for the region.
Cool. And the other thing is, with the relationship between the hypoxia and the drug, is the drug does the drug reach the tumor through the blood supply?
Yeah.
So then wouldn't that explain why if you had low blood supply, you'd have low oxygen levels?
Exactly.
Yeah, okay.
Yeah.
Great, thank you.
Yeah, very nice. Can you go back to the list of list of things you wanted to do?
Okay.
I think
Yeah.
this one there, yeah. So we have to be careful that this is not too much for this project. So first of all, you had to write a proposal to get all these aspects in. This is really nice. But now if it comes to the final report, we should be careful. This is too much. This looks more like a 2-year master thesis. Maybe this is your 2-year master thesis. I don't know.
So actually the last point is just an extension of what maybe the results, but I don't intend to, for the project, for the final report, I don't intend to go beyond the bullet point 3.
That sounds really good. Yeah, that's what I thought as well. So develop the model, you look at some data which you can find some, and then do some sensitivity analysis.
Yeah, and that's all.
And that's all. And I would be very happy with that. Yeah.
Okay. Thank you.
Yeah, thank you very much to the both presenters. Now let me check the participants if my possible presenter number 3 is here.
I've dropped a message for her, but she hasn't responded yet.
You know her?
Yeah, I know her.
Oh, interesting. Okay.
Yeah.
So if you see her or know her, tell her that it's not too late. She can still do it. Okay.
All right. Thank you.
All right. Yeah. Okay. So then we move on to the class. So now I want to share this thing here. Okay, so now we should be on my slides here. I think we are. Yeah, okay, good. So October 15 class. So what do we do? Today I said we do parameter estimation. So the idea is, well, I tell you the idea in a second. This is not 1.3. What's my numbers? Oh my goodness, now I'm confused with my numbers. Is this 3? Parameter estimation. Yeah, I think 1 was introduction, 2 was chemical reaction kinetics. So it must be 3. Yeah, the thing is, we heard about the mathematical models in the previous 2 talks, and also in these conferences, if you attended these meetings. The question is always, how do we relate these to the data? Right, we have a differential equation that makes nice curves, but how do we relate this to the data in an optimal way? And then how do we find the parameters in an optimal way? And yeah, for this, there are many methods available in the literature. And I will only do one here, which is the Archaiki Information Criterion, AIC. There's also a BIC, which is a Bayesian Information Criterion. And recently I've seen another IC, like an OIC or something. So there are many, and there are thick books about all this kind of topic. What I like to do is to at least choose one of them, the AIC, not only to teach you the AIC, but also to prepare the language. So the language changes. We are not talking about solutions of ODEs. Now we talk about probabilities and optimization of a likelihood and things like that. And these are words and terminology you need to learn because it will show up in many of these papers which we read. And it then gets you prepared. If you then need to read about the BIC, then at least you have heard about the language that is used in this context a little bit. So this is based on a chapter 7 in my book, a course in mathematical biology. It is De Vries et al. A course in Math Bio. It is published in SciEM 2006. And now what I did is, or actually Sumaira helped me, we uploaded the corresponding PDF file in our course page. Okay, if you go to the graduate fields, graduate course, and then you click the link for students who take it for credit. So I put much more information under that link, in particular some papers and this book manuscript as well. So I just ask you kindly to use it among yourselves and not sell it on YouTube or wherever you sell this. No, not on YouTube, but okay. So I trust you. Just use it for yourselves, and then it will be fine. Okay. So back to the problem. So assume we have data from an experiment. We want to develop an ODE model and then fit it to the data. How do we do that? And so let's assume we start. So yeah, first we have the data, of course, data observations. And then we come up with a model. And let's say it's an ODE. For example, it could be the oncolytic virus model, which we started with. And then this model, if you go back in our notes, it has parameters. Right, it had interaction parameters and growth rates and all this stuff. And we called them A, B, C, and D in that section. Okay. So here I should say maybe E, G as an example. So then P I use for the vector of all parameters which are in the model. So little p is not just maybe one parameter, it could be a collection of different parameters. So then in general, P is an element in Rn, where n is the number of parameters that we have to worry about. So now we would like to choose the parameter in the best possible way. And there the assumption is that the data we observe are typical to this experiment. Okay, so if you repeat the experiment, you will probably get data in a similar way If not, then either the experiment is not good or the measurements are not good. So we assume, and I think this is a big, important philosophical assumption, we assume that the data are typical for this experiment. So which means if we repeat it many times, we should get very, very similar data. So then what is a good parameter P that fits the data best? And we need a quality measure. So we need a quality measure, which tells us how good that is. Okay, and you might say, why not use least squares, right? You all have heard about least squares. You just square the distance between the model and the data, and then you square this, and then this is your least squares. And you are right. Okay, so the least squares can be derived or will be derived today from this more general setup, which I'm preparing here. So we need a quality measure, and for now I call this a fancy L, P given data. So what this is it is the likelihood that the parameters P are chosen perfectly given the data. So this is called the likelihood. And this will be our quality measure to decide how good our fit to the data is. And a way to compute the likelihood is flipping this around. So as we say, the data are typical for the true parameters, then we assume this, that the likelihood to find the likelihood that the data are P, no, what? No, sorry. The likelihood given the data of the parameters P is a probability to find the data given the model with parameters P. So we flip around the condition. We look at the probability to find the data given these parameters P. And this is what I said earlier, that the data are typical for these parameters P. All right. Okay, so let's define this now mathematically, and then I do an example. Yeah, so I can do next page. Page, annotate. Yes, let's do it here. So definition. So P are the parameter values in Rn. And I consider a function L from Rn, so from all the parameters, into a positive cone, which maps the parameters pi in Rn to the probability to find those. To find given data. So L of pi equals, let's see. So the probability, that's what I just wrote earlier, finding the data for these parameters pi. And I use pi and p for these data, for these parameter sets. So then L is called the likelihood. So who has heard about likelihood before? Actually, I cannot see your images, so if you raise your hand, I cannot see it. But anyway, so raise your hand in front of yourselves if you have ever heard about likelihoods. Now, it turns out likelihood is a little bit cumbersome to work with. We will see in examples why. So people always use the log likelihood. And so that's another important thing. And you just take the logarithm of this. So you do ln of L of pi. And then this is often called the double L of pi. Now the logarithm is a monotonic function, right? So later we use for maxima of the likelihood, and then maxima of the likelihood or maxima of the log likelihood will be the same points. Just because ln is a monotonic function, so then the maxima will not change. Okay. So a parameter pi hat that maximizes L. So it maximizes the probability that the data are represented by these parameters, or LL, same thing, is a maximum likelihood estimator. A maximum likelihood estimator, no closing bracket, just like this. And this is what we are after. So we want to find, so once we have this function L, we can easily take the log, everybody can take the log, and then we can find the maximum. Well, we use calculus, right? We differentiate, we find when L prime is 0, and then we show maybe with the second derivative test if it's a maximum or a minimum. So this is then really just standard calculus stuff. Let me give you a nice example. We do several examples, but the first one is the simplest one, time to cell death. So this comes back to the very first lectures where I talked about probabilities and rates. And we had a simple model for the cell death, which we could describe with a probability to die or with a rate to die in a certain time interval, etc. So let's start with the model. Okay. Okay, yeah. So let's start with this model. P dot is minus mu p. I just realized that now I use P for the population, whereas here I use P for the parameters. Can you forgive me? Please forgive me. This is unfortunate, but if I change it on the fly, I may make it worse. So for this example, P is the population and mu is the parameter. So I'm sure you will manage this intellectual exercise to call mu the parameter now. So mu is the death rate, right? And we talked about this model many times. And yeah. And so then we can solve this. P of t is the initial condition, P at 0, e to the minus mu t. Right? So this is, so mu is constant. Then this is the solution. So then this is the survival probability of the cells. And I need the death probability. So let's look at the death probability. And I call this d of t, which is 1 minus p of t. Okay. And then I can sub it in. So then this is 1 minus p0 e to the minus mu t, just like this. Okay. Now I need the probability density for this d. Okay, so d is a death probability. The probability density would be the time derivative of that. So let's write this down. Probability density of a death, little f of t, is then d by dt of this d of t. Okay, now there are too many d's in this. D by dt of d. So the time derivative of d, can we do that? So then here d dot, let's say, is minus and minus gives plus. So this p0 mu e to the mu t. That's a derivative. And we assume that initially the tumor survived. That's where we started. So that P0 is 1. So the probability to have cells at time 0 is equal to 1. And then d dot or f becomes mu e to the minus mu t.
Minus is missing in the previous line.
Yes, thank you. And it is not. Haha, it is not. But thank you, first of all, for the comment. But I get a minus sign from differentiating the exponent. There's e to the minus mu t. And then this will eat the minus sign in front. Would you agree?
No, on the exponential, not the.
Oh, thank you. Good. Okay. This one.
Yeah.
Yes. Thank you very much. That's right. Good. And so then we have f. Another page. Here we go. So this means that death is exponentially distributed. Let's call this IE. Okay, and 1 over mu is the expected survival time. So yeah, this is not entirely new to us. So this is stuff, as I said, I did in the first lecture where we talked about survival time analysis. So then this 1 over mu is the expected survival time. And we call this this here, this is the probability density of an exponential distribution. Okay, so now let's come to the data. And let's assume the data are that we just observe when cells die. Okay, so we start the experiment, we call this start time to be time 0, and then just we look for at the time interval and mark the times when individual cells die. And then we can measure these times. So suppose n independent cells. And maybe they're exposed to radiation or some chemotherapy or something. So they die at ages A1, A2, and so on, AN. Okay? And so this could be like hours. So maybe first cell dies in 2 hours and 5 minutes, and the second one in 1 hour, 30 minutes, and the last one in 4 hours, etc. So these are the data we're looking at. So the expected survival time from our model is 1 over mu. Okay, so then any of these AI should be kind of a measure for 1 over mu. But of course, the AI are all different. One is 2 hours, one is 1 hour, one is 4 hours. So then what is the parameter mu? What is the parameter mu? So what we have to do is we have to do some averaging over the AI. And there are at least 2 ways how we can do this. So the question is how to estimate mu. So actually I can also write mu is proportional 1 over AI, if you like this better. But this gives you 2 possibilities already. So in the first line here, you can average the AI and then do a 1 over to get mu. Here it indicates you can average the 1 over AIs, okay, and then you find mu. And is this the same? Well, let me write this down. So 2 possibilities. One is average the 1 over AI, 1 over A1, 1 over A2, 1 over AN. And then set mu1 hat to be the average, so 1 over n of the 1 over AIs. I is 1 to n. Okay? As a notation, hat is always used for an estimator. So this is my attempt to find the best possible mu. This is an estimator, and I take the average of the 1/overs of the AIs. Or, second, we can first average these death times, AN, and then we write mu2 hat is just 1/A bar, where A bar is this average, 1/n, sum of the AI. I is 1 to n. Okay, so we have two estimators, mu1 hat, mu2 hat. Who thinks they are the same? I hope nobody thinks they are the same, right? Averaging the 1/overs or averaging the AIs. This is, well, maybe there is a case where are the same. If the A's are 1/2, maybe. If everything is 1/2, I don't know. But in general, I'm pretty sure you're easily convinced that they are not the same. So mu1 hat not equal to mu2 hat in general. In general, okay. And maybe there is a third way or a fourth way or a fifth way to do that as well. Okay, so which is better then? Which do we choose? Which do we choose? And my general is unreadable. Let me fix this. General, good. Yeah, and we choose, we find the right one using this maximum likelihood idea. So likelihood enters L of pi. Okay. So what was this? Let's go back. What is my L? L here. So here, this is the probability to find the data given this parameter. And the probability to find the data, we actually computed. We computed this here, where we said death is an exponentially distributed process. So we use this F. We use the probability density of death of the death event. All right. So then the likelihood would be the probability density to observe death of the first cell times the probability to observe death of the second cell at A2 and the third one at A3 and so on to the last one at AN. And we do the product because we assume all cells are independent of each other. So these are all independent events. And if they are, we can do the product of all these probabilities. Okay. So let's do that. So now the F is mu e to the minus mu t. But now we can sub in all the A's. So let me do that. We get mu e to the minus mu A1, mu e to the minus mu A2, mu e to the minus mu AN. And then we can write this in a similar form, I guess. So we get mu to the n up front, and then the exponentials, we get an exponent of the sum of all these entries. So exponential minus mu sum of the AI, I is 1 to n. Okay, right? Yeah, this is what I have, and this is what we get. And now comes the trick with the log. So now it shows why the log is better. So let's do LL. LL log likelihood of the parameter pi. And now I can call it mu. Yeah, I should have called it mu earlier too. So the parameter is really mu. Let's do this here too. Mu. So taking the log, okay, by the log rules, we get then what we get? We get n times ln of mu minus mu, and then the sum of all these I is 1 to n AI. Right, and then yeah, this is exactly what we get. So this looks a little bit simpler. That's why people use the log likelihood. So from the exponential, you get a sum, which is nice. Okay, back to our theory. What do we have to do now? This one, maximum likelihood estimator. So we have this function now, ln L of mu, and we need to find the maximum. Aha, here we go. Function, maximum, easy, everybody can do this. So let's do that. So d by d mu, right? D by d mu of this log likelihood thing is then differentiating log is a 1 over, so 1 over mu minus, and then here is a mu just as a factor. So we keep the sum of the AIs right here. And then for finding a maximum or minimum, we set this equal to be 0. Okay, and then we can solve this for mu, I guess. So then mu is moving the sum over, moving the sum over, dividing by n. I need to do this in 2 steps. So 1 over mu is 1 over n sum of the AI. And so then mu is the inverse of that. So 1 over n sum over the AI inverse. I is 1 to n. Okay. And now, so this one we have seen before. This should be one of the estimators I proposed. Let's go back. So what is this? This is the second one here, right? We take the average of the AI and then we do it a 1 over. Let's check again. Yeah, so we take the averages of the AI, multiply with 1 over n, and then take the inverse. So this was my second estimator, U2 hat. Okay, so it looks like U2, mu2 hat will be the winner. We just want to check that this is indeed a maximum and not a minimum. So we check the second derivative, d mu square of L of mu. So we just differentiate this again. We get here a minus n over mu square. The second term has no mu anymore. So that's this, which is negative. So making mu 2 hat maximum likelihood estimator. Okay, so that decides which of the two we have to use. All right. Going back to those 2 cases here. So this one. Who would have guessed? I don't know. Would you have guessed that this is the right one? So then I have a little example. Where's my example? Here. Let's put this into numbers because I want to be more specific later when we do confidence intervals and so on. So example in the example, let's say we have the death times of 1, 15, 3, 16, 18. Let's say these are hours, so the cells survive 11, 20, 14, and 13. Apparently, my experimentalist was not able to measure half hours or minutes. So these are all integer hours, but that's fine. So these are the AI. Okay. So then we have to build the average of the AI, 1 over n sum of the AI, which is 12.3 repeated. And then mu hat 2, the estimator number 2 was 1 over a bar, which is 0.081. So this is the death rate in that experiment. And the maximum likelihood, the maximum log likelihood using this estimator is minus 31.6. This is something we haven't done in the theory. So we find mu2 hat, and of course we can sub it back in here. Okay, mu2 hat everywhere here, and then we get a value for the log likelihood, and this value here is minus 31.6. Okay. So we find an estimator. Now let's talk about confidence intervals. So confidence intervals is an interval in parameter space where you can be confident, let's say with 95% certainty that your true parameter is in this confidence interval. Oh yeah, here I have a definition. So define this. Given a confidence level, gamma, and this could be 0.95 if you want to be 95% sure, or it could be 0.99, right? If you want to be 99% sure, it could be any other reasonable thing. It could be 0.9, it could be 0.9999999. So an interval P minus and P plus. So in the parameter space that covers the true parameter P, covers the true parameter P with probability gamma. Is called a confidence interval. All right, so how do we find this? To find this, I use the same example I just did with the cell death. So now I want to find a confidence interval for the mu, which we used. So example, cell death experiment. So we had a maximum log likelihood to be minus 31.6. So let's draw a picture first. Let's draw a picture of what I want to do. So here I have mu, and the log likelihood was a function of mu, and we found one maximum. So near the maximum, it will look like this. And so let's say here's the maximum, which was at 0.081. This was our mu hat 2. And the value at the maximum would then be minus 31.8. So here's the LL of mu. Okay. So what I'm now interested in to find an interval of these parameters, so maybe mu minus here and mu plus here, which covers our best estimator of 0.081. Yeah, and then cuts the likelihood here and here. So maybe it cuts through like this. And so in the end, I'm interested in this value here. Okay, if I know the spread in the log likelihood, I can project this over to the spread in the mu's, and then I can find mu minus and mu plus. So that's what I try to do. Now, to do this, we need some information about the log likelihood. In particular, we need to know how this curves here near the maximum. And there comes another important statistical assumption here, because we assume that the log likelihood is chi-square distributed. Okay, so in most cases, okay, we assume that the log likelihood of mu is chi-square 1 distributed. If you have done courses in statistics, you know that the chi-square distribution is used a lot in hypothesis testing and statistical testing. And this is the case here as well. Now, this also shows you a little bit the problem with statistics, because you do assumptions which are sometimes true and sometimes not. So far we assumed that the cell death is independent, which might be true or not. It's exponentially distributed, and now we assume the log likelihood is chi-square distributed. It's a standard thing to do, so we do it. And then chi-square 1, this has the index 1, which means 1 degree of freedom. Which is the index down here. So then what we do is we use the chi-square table to find this missing information, which are indicated with a question mark here. Okay. So for example, again, we choose a confidence interval. Let's now be specific and call this 0.95. And then this gives us a tolerance alpha of 1 minus gamma, which is 0.05. And this is where we evaluate the chi-square. So we use a chi-square table. And we find chi-square at 1 gamma at 0.05 is 3.84. Magic. So have you ever seen a chi-square table? Maybe I just want to find a chi-square table just quickly here. So just go to Google, chi-square table. I find this a little bit archaic to look at chi-square tables, but anyways, maybe this one. This is readable. I make it bigger. This is even more readable. Hey, this is perfect, because the green highlights the column which I need anyways. So we have degrees of freedom here on the left. We look at 1 degree of freedom because we have 1 parameter to worry about. And then for the different values of alpha on the top, we go to alpha 0.05. And then under 1 degree of freedom, we find a 3.84. And that's the value I give you. Okay. So if the alpha changes, this value changes. And if you have more degrees of freedom, this value changes as well. Yeah. All right. So this is where we get this from. Let's go back to my presentation. So this is the value I used right here. Okay. So now we subtract this value from the maximum, from the 31.8, to find this question mark value, which I had here. Okay. So there's still a space here a little bit. Okay. So now subtract 3.84 from max likelihood, or max log likelihood. Okay, what do we get? We get 35.44. So then what is this again? 31.6, which was negative already, minus 3.84 is then 35 minus 35.44. So I can go back and I call this here minus 35.44. Okay. So then the mu minus and mu pluses arise for those values where the log likelihood equals these numbers. Okay, so then we find mu minus and mu plus from solving log likelihood of mu minus equals log likelihood of mu plus, which equals minus 35.44. Where did the minus sign go? Come on. Or in general terms, this is the maximum likelihood of mu minus the chi-square value corresponding to this alpha. So I think the principle is now very clear. And then we find, so you can solve this. Insert page. How much detail do I want to give? Let me just see here. Yeah, we can do this in our cell example explicitly. In our example, we had n ln of mu plus minus mu plus n times a bar equals n ln mu minus minus mu minus n a bar is minus 35.44. And then we can find this maybe, I think this is an implicit thing, right? It has a logarithm. So we need an implicit solver. Mu minus is 0.027 and mu plus is 0.18. Okay, go back to my graph. Yeah. Well, no, I don't go back to my graph. So so then the 95% confidence interval is yeah 0.027. Yeah, and 0.18, and the maximum likelihood estimator nu2 hat was 0.081, which of course is right somewhere in there. It's maybe even the middle or pretty close to the middle. Yeah. So this is how this is done. Okay. Any questions before I continue? Okay. So one comment again, this is all related to the log likelihood. So this is all related to this idea here in the box, how to come up with the log likelihood. And we came up with the log likelihood as a product of all these Fs. And then the rest is just calculus, finding maxima, finding intervals, and so on, and using chi-square distribution. So the key is to find the log likelihood. And of course, I use the simple model where I know that the log likelihood is also simple. If you have other models, it might look different, right? Or it will look different. And in some cases, it might be actually rather complicated. So here it's all manageable. You have to do it sometime, do some real data, try it out, and then you will see how this works. All right.
The degrees of freedom.
Degrees of freedom.
Yeah, the chi-square degrees of freedom. How can I understand them in terms of what dimension of the problem? What are
Very good. You have a very good question. So this is the number of parameters. The number of parameters you want to estimate.
Okay.
So I had mu was 1, so I have 1 parameter. In the oncolytic virus model, we had A, B, C, D, so we have 4 parameters. So the degree of freedom is 4.
Okay, and after this detailed analysis of log likelihood, is it possible to consider alternative? Like you mentioned, least squares. So I may set some criteria of threshold or something, distance between the data and what the model gives me, the parameter. Is this?
Yeah, these are very good questions. So I think I hear 2 questions in your question. One is, how is this related to least squares, which I do next. And indeed, we can set constraints on the distance of points and model. We can also look at variations of the model and see if it is better if we add a term, or if it becomes better if we do an exponent or something. So all this can be done within this framework. Yeah.
Of course, the log likelihood is established statistics. in
Yes.
estimation. So I'm not going to suggest a derogatory criticism of it, just to consider alternatives.
Yes. Okay. So let's come on to the least squares method. So what does least squares have to do with all of this? Least squares we often use if we have time-dependent data. So now I assume at the time points T1, T2 to Tn, I have measurements x1, x2 to xn. So people call this longitudinal data. Okay. And then which are fitted by a model. Which are fitted by a model. F of Tp, where P again is a set of parameters. With parameters P. So typically in our case, F would be a solution of a differential equation or a system of differential equations. It depends on time. And so then we assume or hope that the measurements are somehow given by the model at the points Ti, for I is 1 to n. And then again, the question arises, what is the optimal choice of P to make this fit possible? Okay, so here we do a number of assumptions. Next page. So we assume. So first of all, that the xi, the measurements are independent. This is always an assumption, and it's almost always wrong. I think, in particular in cancer, for example, I don't think that the cancer cells react independently, let's say, to radiation. But this is simply what everybody assumes. So we do that too. We assume they are normally distributed. Now, this assumption is better because we have the law of large numbers. So if you have a large number of cells, you can safely assume they are normally distributed. For example, a tumor has like 10 to the 8 cells. This is a large number. And normal distribution then is a very good assumption. And then we assume the expectation of the experiment is mu, and we take the observed, we take the model value as the expectation in our normal distribution. And we have a variance, right? Normal distribution is defined by the expectation and the variance. So the expectation is mu, and the variance, sigma, is unknown, but constant. So here we assume we have a given variance. Maybe that's the variance of the measurement which we use, or the measuring device which we use. And is constant, but we don't know the value, and we don't need the value either. So essentially, we assume the xi, these measurements, are normally distributed, where the model is the expectation, and the variance is called sigma square. It's just constant. Okay. So this gives us essentially two models already. So we have two models here. One model is our F. This is the model to describe the data. But then also we have a normal distribution here. So this is a statistical model which describes the distribution of the data points. So I think, at least for me, it was helpful to understand this as really two models happening. So we have a statistical model here. Statistical model which describes the distribution of the data points, and we have F. Maybe be specific. Let's call this the ODE model, which we are typically concerned with. So 2 models, right? And again, could be different. We can change the ODE model. We can also change the statistical model if we have reason to do so. Okay. All right. So let's find the likelihood then. So the likelihood, now we have 2 parameters. We have the mean and the variance in our distribution here. So this is the probability for observation is equal to little xi, for I is 1 to n, given the parameters mu and sigma. And we do the same thing as before. We assume the xi are all independent, so we can write this as a product of n terms. And each of the n term is now a normal distribution. And we know the formula for the normal distribution, don't we? Maybe you don't know it by hand, but you know where to look it up. So the product means they're all independent, and now we use the formula for the normal distribution, which is 1 over root 2 pi sigma e to the minus xi minus the expectation, which is now the f TIP all squared divided by 2 sigma square. Okay, so I just use the formula for the normal distribution here. All right. Good. And then we can do our log, right? Log likelihood, LL, of these 2 parameters, mu and sigma, is then, again, the product becomes a sum. The sum has some common terms. So how does this go? And there's a minus sign, so we get minus sum I is 1 to n of the log root 2 pi times sigma, all in the logarithm, and then minus, what do we have here? 1 over 2 sigma square as a common factor. Sum I is 1 to n xi minus f TIP squared. Yeah, and the little p is mu sigma, so I could write this maybe down here. Mu sigma is the set of parameters. No, hold on. Now I messed it up completely. Oh God, oh God, oh God, oh God. Everybody leave the room. I made a big mistake. Earlier I said I have 2 models. So I don't know, maybe I want to highlight this. This is a wonderful mistake. So wrong. So this is the parameters for the ODE model. And these are the statistical parameters. So this is not the same at all. Okay. Yeah, sometimes it's good to make a mistake, so you can make a point out of it.
Can I make a comment, folks?
Say this again.
So it's Vova. Good morning.
Vova, hey Vova, here you go.
Just want to make a comment on your log likelihood.
Yes.
Yeah, in statistics, like I understand, it doesn't matter if it's sigma or sigma squared. But since you probably are going to, like, I see a log likelihood for normal sample, yeah? So usually we write sigma squared because eventually you are going to differentiate with respect to sigma squared, not with respect to sigma. Do you see
I
my
see.
point?
Yeah, to the mean square displacement. Yeah.
Yeah. So
Yeah.
when we, no, for mu is okay, but we usually write LL of mu and sigma squared, because eventually we will differentiate with respect to sigma squared.
Oh, I
It's
see.
a
Okay,
matter
yeah. So,
of choice.
yeah.
It's a matter of choice, but in statistics, it's just more customary, and you just hit your audience with the fact that it's sigma squared that is the main parameter. Yeah, do you get my point?
I get your point. So we can do that. So we can call it sigma square, sigma square. Yeah.
Dankeschön.
Yeah, no, that makes a lot of sense. Although I will not optimize sigma, I will not estimate the variance, but I will estimate the expectation mu. Okay. So thank you for this comment. So, but now maximizing, right? See, the idea was to maximize the log likelihood and look at this formula. Where can we maximize? So now we want to maximize the parameter p, right? This was our interest, this p here. So the first term only has a sigma. I assume sigma is given and constant. So the first term is just a number, maybe some negative whatever number. Okay, and then this guy here is a factor, 1/2 sigma square. If sigma is given, this is again a number. So what we maximize or actually minimize, and here's a minus sign, important. So what we minimize is the least square error, right? This is actually the square of the errors. And so we minimize, we minimize the square error to get the maximum likelihood. So it falls right out of this. It comes right out of here. So to maximize the log likelihood, so let's call it mu and sigma square, we minimize the last term there, which is sum I is 1 to n, xi minus f of ti p square. And this is, in fact, the least square error. So isn't it nice? So from all this blown up kind of log likelihood thingy, we can generate the least square error under very natural assumptions. So this should be an R. Yeah. So that's what we just did. Nice. Yeah, and the assumptions were, of course, a normally distribution, right? So this gave us the explicit formula using the normal distribution. Okay. So that's this. Oh, I'm just looking at the clock. So we are essentially done for today. Is this a good point to stop? This is a okay. Give me a minute, okay? Give me a minute, and then I stop. Page annotate, because I just want to talk about variable variance. So if we have some reason to assume the variance is a variable, if variance varies, then each of the measurements has their own variance, and we assume the xi are normally distributed with the expectation from the model, and the variance is now sigma I square. And then we in the sum here we get just the sigma I in the denominator. Okay, and if we then find the maximum, we carry the sigma I through, so the sigma I doesn't get out of the sum. And I just give you the result then. So then we get the weighted least squares error. Which is sum I is 1 to n, xi minus f tip square over sigma I square. And then we want to minimize this thing. Okay. And this is relevant particularly for growth curves. So for example, you have a petri dish of cells, and then you measure how they grow. Then typically at larger population sizes, you also have larger variance, whereas at smaller population sizes, you typically have smaller variances. And so, yeah, and then if you do a fit through this, you can take into account that the variation And the small ones and the large ones are different. And these are the different sigma i's. All right. So this is what I wanted to do today. So then I finish. Any questions?
The assumption of normality breaks when you look at cancer stem cells, that the population is much smaller than the tumor.
Yeah, I think you're right. Yeah. Yeah.
The other curiosity or anecdotal comment is that the sum of squares is a big topic in mathematics, and I've
Yeah.
read very complicated seminars about it. But actually, the least square tries to simplify the normal distribution expression there, the exponent.
Yeah. Yeah, that's a good way to see it. Yeah. And now Vova just came in to correct me, and now he left again.
Yeah, he just went before the coffee, he wanted to be a little bit gymnastics.
I see.
Not gymnastics. He also told you Dankeschön at the end. So I guess
see.
it's a big thank you for your lecture.
Thank you. Good. Okay. So then I see you again on Thursday. Thursday, I'll be there in person.
Okay.
Thank you. Thank you.
Oh yeah. If you are not running, you can write that link to the Grads